theta equals e to theta times tangent theta minus theta. Fine. Good pick. I don't think anyone picked that either. Good. So first of all, I look at the function, I see if I can simplify it, and then I have to identify the rule or rules that need to be applied here. There is nothing I can do when it comes to simplifying it, so now I have to identify what rule is applicable here. Can anyone tell us which rule?
Yeah, it's multiplication, so we'll be using the product rule.
Very good. So then this is function 1, and this is function 2. You do not have to switch to my method. I just like 1, 2, 1, 2. But it's up to you. So we want to differentiate the first function. What do we get?
E to the theta.
Yes, e to the theta, and we copy the second one. Now I copy the first one, and I differentiate the second one. Tangent, secant squared indeed, minus theta, yes. What we can do here is just simply factor out e to theta, and all we have to do is tangent theta, just write this, plus secant squared theta minus 1. And there is nothing else we can do.
Would we have gotten points if we didn't simplify it to the...
I will make sure that I explain that, or I clarify it, and it's in the requirement of the problem. But here, for example, it's really not simplifying, because there is nothing much I can do other than just factor e to theta. Okay. So from algebra skills, when we look at something like this, we should say, well, okay, I can factor out e to theta, but it's not a big deal because we can't do anything else, really. Good question, thank you. Okay, I think it's my turn to choose. I will choose 13. So 13 is f of theta equals sine theta over 1 plus cosine theta. Like with any function, we're asked to differentiate. We want to look and see if we can simplify it. Can we simplify it? Not really. So let's identify the type of, or what it is, and then what rule applies here. And I'm sorry I gave you the hint. What rule applies here?
Separation or proportion.
Yes, perfect. Good. So then we have to write the denominator squared. Well, we differentiate sine, and we get
cosine.
Yes. And we have to copy the denominator. Do not be tempted to simplify. Minus. I copy the numerator. And now I differentiate 1 plus cosine, and I will put it here. When we differentiate 1 plus cosine, what do we get?
Negative sine.
Yes. That's it, because 1 prime is 0. Good, so let's try and see what we can do here. Cosine times 1, cosine times cosine, and then plus sine squared over 1 plus cosine theta squared. But how much is cosine squared plus sine squared?
One.
Yes. So I have 1 plus cosine theta. I don't like this, but because the denominator was like that, I did twist it in. So what would you say we can do here, or we cannot?
You can simplify.
Yes, I can simplify, and I will simplify one of those. Put 1, because I've seen 0, so please be careful. So this is it. So it's 1 over 1 plus cosine cosine theta. And this is the final answer. Any questions on this? Any questions on this? Okay, let's choose other problems. We can prove these, but we already did tangent, so it's the same way. Do we want to pick something else?
22 with 3 Fs.
Which one?
22.
22, very good. Let's look at 22. And 22 is f of t equals t e to t cotangent t. It's COT, yeah, cotangent. Perfect. Okay, this is an interesting situation in which we cannot simplify. So I need to identify what I'm looking at. Well, when I try to identify what this is, I have to choose. I will have to say either, there are many options. I will say this is my function 1 and this is my function 2, but my function 1 has function 1 and function 2. We have never seen a product of 3 functions. I can give you the formula, but that's irrelevant. You don't have to memorize something like that. It doesn't matter. I'll show you. But so now I have to choose because I have 3 functions. 1, 2, 3. I either group the first 2 and say this is my function 1, and I have to use the product rule. And I choose the last one as function 2, but remember I have to use the product rule. So I will use the product rule, and inside this, number 1, I have to use the product rule again. So, f prime of t. I will differentiate the product times cotangent t plus t e to t times cotangent prime, which is negative cosecant squared t. Cotangent prime is negative cosecant squared t. Now, in here, I have to use the product rule. Every time I use the product rule, I have to have a sum of 2 terms. So, let's differentiate the first function. What do we get? Sorry. When we differentiate the first function. 1 times e to t plus t. Now we differentiate the second function.
E to the t.
E to t. This is it. I will have to clean it up a little bit. And maybe just remove parentheses, nothing else. E to t times cotangent t plus t e to t cotangent t, and this is negative t e to t cosecant squared t. So what is the formula? The first function prime, the first function prime times the second times the third, plus the first times the second prime times the third, plus, minus, in this case, the first, the second times the third prime. So in other words, what I'm saying to you, you don't have to memorize this. 1 times 2 times 3 prime is 1 prime times 2 times 3, plus 1 times 2 prime times 3, plus 1 times 2 times 3 prime. So in order from left to right, the first one is differentiated, the second one is differentiated, the third one is differentiated. Any questions so far? Any questions? Now, this section ends with some limits, but I'll let you choose if you want to practice more, or I can move on and continue with the limits. And that will be the end of this section, 3.3. So you tell me if you need to practice more. How do
I'd
you...
be fine moving on to the limits.
Okay. Good. So we are looking at something that I mentioned to you last week. The limit of sine x over x as x approaches 0. Okay, I have a limit. What do I have to do first? With limits, always.
Okay then.
Yes. What do we get?
One over 0.
How much is sine 0?
Zero over 0.
Good. Now, a few minutes ago, we had this wonderful discussion about our friend L'Hopital. He said, if it's a limit and you get this or this, then you can apply the rule. Okay, it's a limit, and I got 0 over 0. So now I can apply the rule. Let's find the limit. This and this are both hypotheses. It's a limit, and it's 0 over 0. Limit as x approaches 0. Can anyone give us the derivative of the top?
Cosine.
Yes. Can anyone give us the derivative of the denominator?
1.
That's it. Plug it in and tell me what is the limit.
1.
Exactly. So this was a perfect example, right? So what we need to remember from here is the fact that not just this, not the fact that the limit of sine x over x as x approaches 0 is 1, and also limit as x approaches 0 from x over sine x is also 1, using the same rule, L'Hopital's rule. You can determine that that's also 1. But in general case, the general case, what do I mean by the general case? I mean this. Limit as long as these are the same and the limit is obtained when x, or determined as x, when whatever this is, it could be x plus 4. As long as x plus 4 approaches 0, which also means x approaches negative 4. When x plus 4 approaches 0, I move 4 to the other side, and I get this. So as long as these three are the same, and this expression, whatever it is, approaches 0, the answer will always be 1. So I would like us to look at a couple of limits. Here they are. So I would like to start even with 45. So I'm going to copy 45. Here's the first one. So x approaches 0. Sine 5x over 3x. Yes, you can use L'Hopital's rule, but we don't know the chain rule, so we cannot apply it right now. Okay? The next step, we're going to look at 3.11, and then 3.4, which is the chain rule. We don't know the chain rule right this moment. You may know it, but we can apply it right now. Okay, so I have to plug it in. It's, of course, it's 0 over 0, so there is hope. There is hope. No guarantee, but there is hope for this limit to exist. So now I'm looking at this argument. Forget about the denominator. We analyze piece by piece. So I have 5x. Remember, you cannot separate sine 5x, right? It's not sine 5 plus whatever. So this is the argument. the argument has to approach 0. But is it? Yes. When x approaches 0, what will 5x approach?
Zero.
Perfect. So I have a sign in the numerator. I have an expression that approaches 0. I have 5x that approaches 0. But if I don't have 5x in the denominator, I cannot draw a conclusion. So I have this box. I have it. I have this box. I have it. But if I don't have 5x in the denominator, I cannot conclude that this is 1. I don't have 5x, but I have 3x. And I am allowed to multiply and divide by 5. So if I multiply the numerator by 5 and the denominator by 5, am I changing the expression? I'm multiplying by 1. So if I multiply the numerator by 5 and the denominator by 5, am I changing the function?
No.
No. But stay with me. I will rearrange this as 3 times 5x. I can swap these two. It doesn't matter. It's a product. 5 times 3 times x is 3 times 5 times x, is x times 3 times 5, is x times 5 times 3. It doesn't matter. But now I have the box in the denominator. So I have this, which is here. Now I have this, which is here. I have this, which is here. Okay? I'm going to rewrite it because it's not very clear. Too much going on there. So, I'm going to start from the beginning. So x approaches 0, sine 5x over 3x. And I will rearrange it as limit as x approaches 0, 5 times sine 5x over 3 times 5x. I multiplied the top and the bottom by 5. That's what I did. And I swapped these two. I put 3 in front and 5 following. And also, I would write this. Now, I have the box, I have the box, and I have the box. If this were not here, what would be the answer? What would the answer have been? Anyone? Box, box, box. What would have been the answer?
1.
1. So the answer to this, as is right now, is 1. But I also have this. So then what is the answer?
3/5.
Yes. You meant 5/3. Yes,
5/3.
indeed. Indeed. That's it. That's it. I know I have to stop. I don't consider this section complete